Thank you very much for the very kind introduction, and also as I had no idea that what exactly the audience would be, so that I just prepared something which is starting from the very beginning, and also very, very brief on whatever some of the most recent results on the entropy region. Whatever results I'm just going to present you, they are mainly due to Matus, which is sitting here, so that I just made very little contribution for the whole thing. Maybe my contribution is simply just making nice pictures, so that's what I try to do here. So I try to be very brief on the first part, and I will just skip a lot of things. And so if you think that you are not familiar or you want to do something more about that stuff, then please just stop me, and then I will just try to spend a little bit more time. And also I just made 3 lectures. And I want to go through the first very fast and start the second one before the break, so that I will have more time for just doing some interesting stuff before that thing. Okay, so that some basic definitions, whatever the entropy is, whenever we have a distribution, I can go on. Okay, the entropy of a single bit, conditional entropy, mutual information, conditional mutual information, whatever. Next slide. Yep. Any? No. And everyone knows it. Okay. Shannon inequalities. Okay. Here are the Shannon inequalities. The entropy of the empty set is 0. Okay. And the sum-additivity. And the question is that was before the 98. That are there any more inequalities apart from the Shannon inequalities, which are always satisfied by the entropy variables? And of course, the conjecture was that yes. But there was a huge, big search for any of those inequalities, and it was in vain. And it's no wonder. So the complexity of the question is quite big. So the whole question is like, if you know that where to look, then it is easy to find. However, it is a huge, big, high stick, and you are just looking for a little needle in it, then you are just totally lost. And so that's usually the problem around here. Okay, some case studies. And the first question, if I have a single variable, and what is the entropy? And this is, if I have a binary variable, then this is the entropy. I hope that you have just saw that pictures millions of times. If you are just taking several independent variables, then the entropy adds up. So therefore, the entropy of a single variable can be any non-negative number. So that's for the entropy of a single variable. Okay, entropy of 2 variables. Wow. Okay, if I have 2 variables, then I have 3 entropies. Okay, and this is the first picture. So this is how the 3 entropies of 2 variables look like. This is I have some pointer somewhere, so that this is our first variable, second variable, the joint entropy, and whatever the green triangles are, so that you can just think that the green triangles, they are just starting from the origin. Here is the origin, and they are just blowing up this way. So that this is a cone with a 3-sided cone, which goes to the infinity. So that, yep, okay, they are different levels as they are just going up. So that is whatever the Shannon entropies are saying about the 3 entropies of 2 random variables. And what actually happens is that each point, whatever you see here, so that which is inside of this green cone, there is a distribution which realizes exactly that stuff. Okay, another, so that I'm just showing you another view of the same picture, because in higher dimensions we have to just make reductions, and so that they might just help. So the one thing is that I'm just normalizing the thing so that the total entropy would be 1, and in this case I have only just 2 dimensions. Okay, and in this is one thing, and in this case the result is this the result is this green triangle. Okay, so that if I'm just the same cone, if you just cut with AB equals to 1 with it plane equal, then I'm just getting this green triangle, so that if you're just shrinking and growing dense, we are just getting this stuff. Whatever is on the right-hand side, it says that everything is realizable here. Okay, next question. 3 variables. Okay, in 3 variables, we are just getting a little bit trouble because in 3 variables, we have 7 entropies, and showing things in the 7-dimensional space is a little bit problematic. Okay, visualizing stuff. So this is the 7-dimensional cone, and there is a trouble with the boundary, and even it is not known that what exactly the boundary, how the boundary looks like. Ferro, any progress in the boundary of this? Nothing. Anyone knows anything about the boundary of, yes?
Actually, yesterday I talked about this. The extreme rate contained uniform Metroid U23. That's
yes.
It is discrete.
Yes.
And also, I know that Professor Matus has a result that there's a 2-dimensional face. There are some zigzags.
Yes.
Boundary, and
yes.
also I have a result that another 2-dimensional face, there's only half lines entropic, other places are not entropic.
Okay, so that.
This is all the categorization up to 2-dimensional face of gamma 3, but when the number of the dimension greater than or equal to 3,
yep.
all
Okay, I said, yes?
Yeah, I'm a little bit confused. So is it true that for 300 variables, Shannon inequalities are enough, right? So you're not talking about the closure, is that wrong?
No closure, no nothing. Exactly, whatever you have. See. So for two variables, everything. Okay, for 3 variables, there are a lot of holes. That's what you have seen. And if the 2-dimensional faces of the 7-dimensional polytope is characterized, the 3-dimensional faces, that's what remained open.
So just to make sure I understand correctly, so the closure of C, we know it, but C itself, we don't.
Okay, for this closure of the C3, we know, and I'm just making a kind of pictures of how the closure of gamma 3 looks like. Okay, so that. So that here are the here are the 3 variables, and I'm just introducing the 7 numbers. Whatever you see here, that's the usual way. And all the small letters, whatever you see here, they are non-negative except for the G, which is in the middle. That's that which can be just -1. And okay. And so once again, we are normalizing that way that the total entropy would be 1, so that ABC equals to 1. And also this A, B, and C, which is just the private information, whatever, we simply just discard them. I will just go back, that's why I can just discard this, whatever is in the A and B and C. So I simply just set them 0. And whatever I just remained is 4 numbers, the E, F, D, E, F, and G, these 4 numbers. Fortunately, the sum of these numbers simply just gets 1, which is the total entropy. And so therefore, I can make a picture of the whole thing as I put weights, these 4 weights, in the points of a regular tetrahedron. And then I'm just getting stuff here. And so that's it. So that, as you see, that D, E, F, and G, so that are the weights whenever they are just coming from the Shannon inequalities. And whatever is inside this green and pink part, that is exactly that what can be just got from the Shannon inequalities. So that is the picture of the, okay, at least a certain part of the 7-dimensional cone, whatever is just described for the Shannon inequalities. So that's it. And also G can be negative, and this negative is simply just the bottom part. This is pink part here. So that's one kind of a picture of the 7-dimensional polytope, whatever we can just see. So not too difficult, but anyway, sometimes it is good to see that, good to know that how it looks like. Okay, a different kind of visualization which comes here is that once again, Okay, no, I am just not throwing away the private information, but I'm just saying that the private information is, I'm making a symmetrization of the whole thing. So that what is symmetric? It is symmetric in A, B, C, and also symmetric in D, E, F. So I'm just using alpha as the sum of the symmetric part. Beta is another symmetric part. And in this case, alpha plus beta plus G simply just gets up to 1. Okay, so that rather than throwing away the private information, I'm just making a kind of symmetrization. So that I'm just searching that what is the how the symmetrical parts look like, and in this case, I'm just getting a different kind of picture. So that in this case, this thing, whatever you see here, is nothing else but the center of the previous picture. And this thing, whatever you see here, it is what is just can got by adding and taking away this private information. So this is a kind of a different picture of the same 7-dimensional cone, which also includes the private information, so that it protrudes from the central axis in another dimensions. Got it? Fine? Okay, so that this is a different kind of, okay, some way we have to reduce the 7 dimensions to something smaller one, and this is one way. So one way is simply just trying to get, to throw away as much coordinates as possible to get something in the middle, or we are trying to make some kind of a symmetrization and also try to look only at the symmetrical part. At least we will have something about the symmetrical part. Okay, so there are two things which can be done, and this is the two different pictures of the 7-dimensional cone. Yep, okay. Any question? Yes, that's fine. Yes, fine, okay. Okay, next question is that the 4 random variables we have 15 dimensions, and the question is how it looks like. And the answer is that no one knows, okay, unfortunately, and still. So that there are two things. This is we have a lower bound, we have upper bound, and they are so far away. Okay, as you can just imagine, that's Europe and America, so that's a very, very huge gap between the two things. Okay, there are some partial results. The closure is convex cone. Okay, proper subset of the cone. This is the very famous result of Zhang-Yeung from 98. So that was the very first result. This polyhedral inner cone, which is just determined by the Ingleton inequalities. This is real subset and the polyhedral cone, and the result is that the closure is not polyhedral, so that it has a certain curve at a certain point. So okay, hopefully I will just be able to show that one. Pardon me?
Before we go to 15-dimensional object, going back to 7-dimensional object, you had 2 ways of projecting them into lower dimensional space.
Yes. Yes.
So the question is, if you really blow them back to 7th dimension, then still we don't know how the
Okay, so more or less this is exact. So we have the equalities of the faces of the 7-dimensional polytope. The question is that how to visualize them, so that how to look at them. So if it is an algebraic question, that there is no question. Okay, you have inequalities and you know whatever the consequences are. If it's a geometrical question and you want to know exactly that how they look like, then it's a different question. So that's what I try to just make pictures. So that if we have, sometimes pictures are more leading and they are giving more information than a bunch of inequalities, but it depends on the people. And okay, anyway, pictures are always welcome, and they are just give at least some intuition and things how they might look like. So anyway, those two pictures, they do not give the whole story. By the way, they are giving some information that how certain cross sections of the 7-dimensional cone looks like. And I showed it because we are just doing the same thing for much higher dimensions. And at least we'll just see that, okay, that how those things, whatever we see, they are related to the big picture, which is just still mysterious stuff. Yes? Okay, hopefully this answers your concern. Okay, 5 or more. Okay, that's 4. We are just very happy, and we are just going going to 5, and for 5, at least according to my knowledge, very little has been done, and this is computational, and so lots of problems around here. So okay, there is some general stuff, which is so you are replacing 5 with a really big number. Namely, the entropy region is that's the conjecture is the entropy region is substantially smaller than whatever the Shannon inequality is allow, but the substantial is simply just exponential in certain places, but no one knows anything about this thing, so that even linear lower bound is not known. So that there's exponential and a linear between anything is possible. The conjecture is that it is exponential somewhere. But okay, so that there is lots of problems which no one knows exactly. For linearly representable distributions, we know that here are some exponential lower bounds, which is just due to Anaga. She is either here or she was here in the last week. At least I saw her picture in the board. Okay, so that's because this entropy distribution, inequalities on the entropy distribution is used in secret sharing. And certain bounds in the secret sharing can be just got by using those entropy inequalities. And the best inequality is sublinear still, and the conjecture is that this bound is exponential some way. So that's a huge big gap, and so that it shows that the inequalities, whatever we do have, should be really very, very far away from where the entropy region is. Yes?
So just to make sure, so the question here is about the existence of a family of access structures that need exponential, or is it any?
Yeah, this family of access structures which need at least not exponential, okay, which needs linear. Okay, that's linear. Okay, that would be okay. That's really big stuff. Even we know much more than this result has been accessed, and so that time so this lower bound, it doesn't use any non-Shannon inequalities. But even having non-Shannon inequalities, we do not have any concrete access structure for which the bound would be linear, at least. Okay, that's even the bound would be better than this log n over log n. That's like if you are just improving this by a factor of log n, then you are the king. Do it. Okay, why not? Okay, so that's some important distribution which will just show up lots of times. I do not know that what is the exact name or how we are calling it. I just learned it from Ferro that it is called the ringing bells distribution. And okay, so this is the simplest way how to define the distribution. Simply just you enlist all the possibilities with the appropriate probabilities. Okay, so that is the whole table which defines you the probability. And the ringing bell distribution is, okay, this is a wrong picture, but this is the best whatever I just thought. It has to have 2 bells, not 4, but 2 bells. Anyway, she's just having 2 hands and ringing 2 bells, 2 of the bells. Okay, what the distribution is that we have 2 ropes. Okay, the 2 ropes are C and D. Okay, and she pulls both ropes with probability 1/2 independently. Okay, the C, as you see that C and D, they are independent, and they have 1/2 probability, so that everything comes with 1/4 probability. And we have 2 bells, the bell A and the bell B. And the bell A rings if any of the ropes is pulled, and the bell B rings if both of the bells or both of the ropes has pulled. Okay, so that A rings if C is 1 or D is 1, and B is 1 only if C and D is 1 as well. So okay, that if you have pulling both ropes, then A and B is rings. If you do nothing, then none of the bells ring. If you are pulling either of the ropes, then the bell A will be ringing. So that's the ringing bells distribution. Okay, that's easy to remember. This is a fantastic distribution, and it comes up as a counterexample in lots of times. So that's a good thing to know. Some of the marginals and some of the entropies of the ringing bells distribution, which I will just go back also for that stuff. Okay, as you see, original entropy is 2. Okay, because everything is 1/2. there is the marginal on BC and marginal on AB, so that is the distributions, and also the entropies are 1.5. Yes, okay, I hope that I did the calculation correctly, so that tell me if some numbers are wrong here. Okay, common information, you know everything about the common information. Yep, okay, so that I just put here that I wanted to introduce the Ingleton inequality. Okay, the common information for two variables is whatever can be extracted of both of them and exactly those things. And okay, that this is the Ingleton inequality, which says that if A and B have common information, then this inequality holds. Okay, and the proof is, okay, here is the proofs. Okay, so here is a 5-variable Shannon inequality. Okay, so that checking a 5-variable Shannon inequality can be done by using this ITIP. Maybe I do not know that how to pronounce it, so that I'm from Hungary, so I say that ITIP. Okay, so that Raymond, how do you call it? How do you call your program? ITIP or ITIP or ITIP or ITIP? Okay, so ITIP. Okay, so you can use it, simply type in, and it comes out. Yes, it's an inequality. So that's simply. And for this, simply just plug in E as the common information for A and B, and you are just getting whatever the top. And also, I would like to call your attention if I'm just here making some right. So I also wrote a program which is a standalone C program, which is a terminal-based version of this ITIP, which you can just download from there. It is runs under Linux, and at least it can check the syntax. I was just very much bothered that I just typed in this huge stuff, and the only message I got is it contains some syntax error. What the hell? So that at least my program simply pinpoint. Okay, here is the error corrected, and also it makes term expansion and so good other things as well, so that it is downloadable from there.
Can you remind us how you define common information?
What I do?
How do you define common information?
Okay, common information. Okay, back common information. If you have two variables, xi and eta, okay, two random variables. Then the question, is there a third variable, which I'm just call here C, third random variable, so that those things are, so that C is determined by Xi, C is determined by eta, so that the joint entropy is the same thing. However, everything, whatever can be extracted from together from C and eta, it can also be extracted from C, which is actually the saying that, okay, that they are, or the joint information of C and eta is exactly the entropy of the C itself. Okay, these three things, so that the C is determined by Xi and eta, and the joint information in Xi and eta can be just found in C. Then C is the common information. So also you can just imagine that Xi and eta is here, and you want to just find something in the middle, which would be, so that these three things would form a Markov chain. Okay, something which makes these two things independent. Okay, I'm assuming that stuff. If you can find such a stuff that you are calling that these two things have a common information, then that is the common information. Okay, typical. Yep.
When you say on the next slide, this A and B have common information.
B, if A.
By the sentence, A and B have common information.
Yes. Okay. This A and B are the random variables. And if these two random variables, they have a common information, you are just coming up with a third random variable, which is a common information for A and B. Okay, if there exists somewhere in the big blue sky something which is a common information in A and B, then you have this inequality. Okay, no matter what. Okay, and it means that, okay, if you have common information, this is a very, very strong assumption on the variables, at least. And so that also, so this inequality is the Ingleton inequality.
Have common information means the entropy of the random C greater than negative, or
This is the common information, yeah?
Yeah. So how does it does not, what do you mean, it have common information or it does not have information, does not have means it equals to 0? Or
No, it means that you cannot find an appropriate random variable. Okay, you have to just come up with a random variable which has a joint distribution with C and eta. Okay, you have to just extend this table, the stuff, and you have to just find out the appropriate probabilities in a certain way. And simply, you cannot extend this, distribution table with a next variable in a way that everything would just fit properly. So that's simply just the moral here. So that simply creating, adding up a new random variable, it simply means that you are expanding the distribution. You have a new variable with a lot of new possible values, and so that you are just adding new probabilities at the end, but you want to keep all the marginals of the old variable to the same what they have been. Question, can you do it? And the answer is not always. At least there is a lot of troubles, a lot of cases when you simply just cannot do it. If you can do it, then it has consequences on what possible values of the entropies of those variables can be. Yep.
People understand common information in a different sense that we are speaking. Either you take the mutual information, which
Yeah.
or you take this common information entropy of this best
Okay.
function of both.
Uh-huh.
And this is smaller than the mutual. And you say
Uh-huh.
the common is equal to the mutual.
Aha.
This is here.
Okay. Yep. No. No. It should be unique. Then it's unique. Yep.
With zeros outside of these blocks, and C the index of this block.
Aha. Okay. Okay. So unique. Okay. Practically, this is unique. Okay. Okay. So Bell's distribution. So I'm just going back to the Bell's distribution. Here are some, and this is the Ingleton score for the Bell distribution. Okay, so that here are the different entropies. Okay, the joint information of A and B is 0.1. And the Ingleton, as you see here, the Ingleton value, what is the Ingleton value? EAB. Okay, so this Ingleton, okay, anyway, it does not satisfy. Okay, that this is the Ingleton inequality, which says that this expression, whatever you see here, it must be non-negative. That is the previous slide, whatever it says. Okay, you see that this expression should be non-negative. However, for the Bell distribution, it is negative, namely the value is 0.0612, whatever, so that you can just compute the whole thing. But at least for the Bell distribution, A and B do not have common information. At least for that thing. And the question is that how bad this Ingleton violation can be. Okay, so we are looking for different values that how much this Ingleton score can be, and whatever I know that we have lower and upper bounds on that for this value, and okay, at least 1 year ago that it was the best upper and best lower bounds for the Ingleton score, and we are just still waiting for champions, simply just giving better upper and better lower bounds for that thing, and you see that these two values are still quite far away from each other. So that's not easy to get something. This is the Ingleton expression. Yeah, okay, so this is the Ingleton inequality, which should be non-negative whenever we have A and B have common information, and so that it has to be normalized in some way. And so that there are the most natural one is simply just take the entropy of all distribution and simply just divide this thing. So that this is This is the Ingleton equality. That's what I try to show there. This is exactly. And so if A and B have a common information, this should be non-negative. and so that how bad the Ingleton violation can be. So that was the question, and the thing is that, okay, at least for this very simple distribution, this is this value. And if you are just tweaking with the probabilities here, then you are getting a little bit better, so that you are getting almost as, okay, 0.08. Okay, so that you can just go to 0.08. Yeah?
Does your example live outside the box? Like exceeds the upper box?
Okay, lower up, okay, absolute value. Okay, by the way.
So for lower bound, upper bound, you're varying these probability. That's what you mean.
Okay, so that I know that this value cannot be smaller than that one. Okay, so that's okay. Anyway, the Ingleton score cannot be below this one. Okay, cannot be smaller than that value. Okay, I have an example when the Ingleton score is that much, but I do not have any example which would be just smaller than that one. Okay, so that. Okay, so that I know I can prove that the Ingleton score cannot be lower than that one. I have an example for that one. But I can neither raise this number, nor can I lower this number. Do something so that, okay, that's quite a huge gap between these two things. We can make these two numbers closer to each other. Okay. Yep. Okay, fine. Okay, so that's for the first lecture. So if you do not mind, then I would like to just keep these 5-minute breaks from now on, and then start at OR.
But I think we probably need to align with the.
Okay. Then I will just start the other one. Okay. Okay.
That's what I was told. So.
Okay, then let's start the second one. Okay, so that short introduction to the polymetroids. Okay, any question for the stuff whatever I just told? Not. And is there anyone who doesn't know what the polymetroids are? Okay, everyone knows. Very good. Then I will just get over the whole thing. Entropic polymetroids, they are polymetroids which are the entropies of certain distribution, and almost entropic if it's in the closure. Okay, that is the closure of the stop. And okay, I'm just showing a short proof of Ferro about that why the entropic polymetroids, the internal part of the closure of the entropic polymetroids is entropic. Okay, so there are no holes in the entropic core. So I'm just showing you a short proof about this fact. Okay, this is at least I didn't find this statement in your book, or maybe it is there. Okay. So that's okay. At least they are quite a short proof, and I hope that okay, you will appreciate the nice way that how it can be just proved. Okay, so that first we are introducing a lot of entropic polymetroids, and they are entropic polymetroids which are just denoted by RS. So S is a subset of the whole base set. Okay, and this polymetroid, it has one whenever the it intersects this S and 0 otherwise. Okay, so that for each subset S, I have a polymetroid, which is once in a lot of places and 0 otherwise. And so that this polymetroid is entropic. Okay, that's the first claim, and the proof is just quite easy. Namely, I'm just taking the distribution which takes only two possible values, either 0 or 1, and each variable has 0 with 100 probability, and each variable has other values. So the whole distribution has only two lines, whenever everything is 0, or when everything is 0 except for those variables which are in S. That is the other kind of things, and so that is the two lines. And if you are just looking for the marginals of those distributions, then the marginal will have entropy 0. if this I and S, they intersect in empty set, because in this case, these two lines will be the same thing. Okay, so that's the marginal. Whenever these blue lines, they are exactly when we have the set S available. Okay, so that if these only two things, then S is simply just set 2, 3. Okay, fine. S is 2, 3. And so these are the distribution. I have just these two possible things. And if I have a marginal which doesn't contain neither 2 nor 3, then the entropy will be 0. Because in this case, everything will have probability 1. If it intersects this set 2 or 3, then the entropy will be 1. Okay, so that this polymetroid is simply the one, whatever I just defined here. Namely, the value is 1 if the base set intersects S, and if the entropy is 0 otherwise. So therefore, this is an entropic polymetroid. Yep. Okay, the next thing that not only this is an entropic polymetroid, but if I'm just multiplying with any non-negative number, then it will also be an entropic polymetroid. So the lambda times SR, this is also entropic polymetroid. And the proof is, yep, okay, so not only just the 0, 1, but with anything else. And the proof is the same thing, whatever. But instead of 2 lines here I have a distribution which has entropy exactly lambda. And I'm just keeping the distribution exactly in the blue columns. And everything else, it will be just a fixed constant value. And in this case, or whenever it is not intersects these blue sets, then the entropy will be 0. If it intersects the blue sets, the entropy will be exactly that lambda. So that lambda time RS is entropy. And also, okay, the sum of entropic polymetroids is entropic because you have to just take disjoint sets. And okay, so that's fine. And the use corollary is that if you are just looking for this cone, which is you are just taking arbitrary constants, non-negative constants here for each subset. You are just multiplying this stuff, then this cone is an entropic. Every point in this cone is entropic. What if you are just choosing lambda non-negative and you're just taking it, then every point in this set, it will be just entropic. Okay, so this is a cone. Okay, that's a full, and okay, that's not only a cone, but this is a full dimensional cone. Okay, so that it has dimension exactly 2 to the n minus 1. Okay, so that's full dimensional cone. Okay, and why full dimensional? Then here is the proof that why this cone is full dimensional. Okay, so that what you have to look at that this RS, this vector RS, if you're just putting down these 2 to the n minus 1 vectors RS, then they are linearly independent. That it simply means that this cone, whatever is just spanned by this vector, is full dimensional. So therefore, these RS vectors, they should be linearly independent. And why are they linearly independent? It's because okay, you are using induction for n equals to 1. The dimension is 1, so that is fine. And for large things, the matrix, if you are just looking for each line, then you simply see that if you're just picking the nth element here, the last element, so this A is the last element, and every subset is either disjoint, it does not contain A, then this is the J, which is disjoint from A. This is the A, the single element subset, and all the other subset, which is containing something else. So these are that how I'm just putting the columns, and this is exactly that how I'm just putting the rows. And I will see that okay, the matrix looks like that here. I have the same matrix what I've had before with one less element. Okay, this is one when they are just multiplying with 0, and here as the subset contains A, and the other subset which should be intersected also contains A, so that I have ones everywhere here. So that this is the matrix, how it looks like for n plus 1. And okay, that's simple matrix manipulation gives you that the rank of this matrix is the same thing as the rank of this one. Simply you are just subtracting this row from every other row below it. Okay, so that the ranks of these two things are the same thing. And also you are subtracting this row from every row to the right, so therefore this matrix has the same rank as this matrix. And if M is full rank, then this is also full rank matrix. Okay, so that is why this cone has a full rank, and okay. And okay, that the theorem, which comes from Ferro, that the internal of the closure of the entropy region is full dimensional. Okay, so internal of the closure is full dimensional. Proof: let G be an internal point of the closure of the entropy region. Okay, this is an internal point of the closure of the entropy region. What the hell? It means that the entropic point, that's a neighborhood of G, so that in that neighborhood, the full dimensional neighborhood, so that the entropic points in this neighborhood form a dense subset. Okay, so that this G is inside the closure of the entropic region. It's the same thing saying that in the neighborhood of G, the entropic points form a dense subset. Okay, so that the G is in interior of the closure. It means that, yeah, pardon?
For any neighborhood.
No, not any neighborhood. There is a neighborhood of G in which the entropic points are dense. You have to just choose a neighborhood of G which is inside the closure. Okay, and if this neighborhood is inside the closure, then inside this closure, the entropic points are a dense subset.
What would be a non-internal point?
This is on the boundary. Okay, that's on the boundary. Okay, there is no neighborhood of G which would just, okay. So that's there is a full dimensional neighborhood of G so that the entropic points form a dense subset. Okay, then you simply just make H minus C. Okay, so you are subtracting the full dimensional cone from this entropic point, this G. Okay, this is the negative of the cone, full dimensional cone. As this is a full dimensional cone, so therefore it must contain one of the points because the points are dense. So there is an entropic point in this full dimensional cone here. Okay, and okay. And since H is entropic, then we know that H plus C, everything in H plus C is also entropic. Yep. Okay. Okay, so that, and G is inside this H plus C. So okay, what we do that here we have a point which is inside the closure, then we are just taking a full dimensional cone downwards. And in this full dimensional cone, we must have an entropic points because the entropic points that's in this neighborhood of this point, they are form a dense subset. If they would avoid this thing, then that would be a whole full dimensional open set which does not contain any entropic points, so that it would just in contradiction with the density of the entropic points. So that there must be entropic points in this part of this cone. That will be H. And if this is entropic, then H plus C, it is also everything in H plus C is an entropic. So therefore, and G is inside, and even a neighborhood of G is inside. So therefore, everything is entropic. So if I have an entropic point inside the closure of the entropy region, then it will be entropic. Fantastic. Thank you very much. Okay.